I'm very happy to introduce the next speaker. We now have contributed talk by Nicole Muecke from the Technical University of Berlin. This is the first out of the 4 contributed talks that we will have in this workshop. The stage is yours. Thank you very much.
Okay, so thank you very much for accepting our topic to this workshop. So today I try to give you some first insights into the influence of overparameterization on distributed learning. So this is a really new topic and a really young research field. So today I'm giving you some first results which I got with my colleagues Enrico Reis, Jonas Rumhagen and Markus Klein from Potsdam University. And so the outline is the following. At first I need to introduce, of course, the setting a little bit. And I'm going to show you then next what the naive approach would be. This is uniform averaging of ordinarily squares, and why this is maybe not a so good idea. And finally, we dive a little bit deeper into some theory and take a look onto the effect of additional regularization on distributed learning. Okay, so at first, what is distributed learning? So distributed learning applies when we have a very large amount of data, and it is a common strategy to reduce the overall training time by exploiting multiple computing devices. So the data is distributed onto several machines, and every computation is only done locally. So for example, locally you run some SGD or some other algorithm, and in the end there is some synchronization step. For example, you take a simple uniform average. So this would be the most simple setting you can imagine here. And distributed learning is, as I said, a very active research field and has seen a very increasing attention in the last years. For example, in empirical risk minimization, in the kernel setting, in fixed and high dimensional setting, and much, much more. And this is just a very small amount of work we have seen in the last years. But also on the other hand, for the overparameterized regime, such as deep learning, distributed learning is far less well developed and absolutely not really understood, but it's also of high practical relevance. And so today I want to make a first step towards a better understanding of distributed learning in this regime. And in particular, I want to focus on the efficiency. That means I want to study what happens with our error bound or with the efficiency when we increase the number of local machines. Okay, and I'm starting to analyze the most simplest setting at first. So I hope you can see my screen here completely. The most simple setting is just prediction in random design linear regression. So my feeling is when we do not understand this simple linear regression setting, then we have not really hope to understand more complex setting like neural network learning. So in this setting, we have a random covariate vector from ID and a response from the real line here. I denote my covariance operator here as the expectation over this matrix. This is a D by D matrix. The optimal parameter vector is obtained by solving here the minimization problem. So this is just the expected least square loss. And my data is here generated by this simple model. The noise variable is just comes from a normal distribution with a certain variance. And by capital X, I denote my data matrix. And by capital Y, I denote the response vector. Okay, so in the distributed setting, I take the most simple division of my data size where I equip just each local node with the data set of the same size, which is n divided by m. And so I need some more notation. I'm sorry for this. The local data matrix here is just denoted with a subscript n. And this is, again, a matrix in R n over m times d, and here the corresponding output vector. So okay, again, so each local node is equipped with a data set of the same size. And on each local node, I'm running some estimator. This can be, for example, in SGD. Today, I'm only considering ordinarily squares or the minimum norm interpolant locally, or ridge regression. And finally, we do a simple uniform averaging here. And this setting is also called communication efficient, because we have at the end only one simple communication step. All right, so I want to say a little bit about the efficiency. That's why I need to introduce also the notion of risk. And I'm considering here just the typical excess risk, which we have, taking here the expectation with respect to the noise. This is then when inserted our estimator, still a random variable, that's why he is ahead. And taking finally also the expectation with respect to the inputs. This is then just a deterministic quantity, and I'm going to analyze two different settings. And so here, the first setting, I'm going to analyze the risk with high probability and also in expectation. Okay, so but mostly I'm interested in the prediction efficiency. So this means I try to compare my distributed estimator with the one which comes from the single machine problem. And somehow we have to define when we say that a method is efficient. And for me today, this means when I have no loss in accuracy compared to the single machine problem, then I say my distributed estimator is efficient. So this means that the ratio here should be close to 1. Is it close to 1? This is good. We have no loss in accuracy. And is it very small? Then we suffer a large loss in accuracy. And I'm very much interested here in estimates of the efficiency as a function of the number of machines. And to give you a first feeling how it can look like, I want to analyze uniform averaging of the ordinarily squares estimator. So this means locally we solve here this optimization problem. And luckily in this very simple setting, our local estimator has a very nice closed form solution. And again, I'm considering here a uniform average. So in the setting where we have small dimension and locally a large sample size, the local risk can be computed quite easily. So because in this setting, we know that the ordinarily squares estimator is unbiased and the risk is just given by the variance part. And then it's very easy to calculate also the global risk. This is just given by this sum here. And under some specific distributional assumptions, we can also calculate very explicitly these traces here. And this is done, for example, in this paper, which you already have seen today for the normal distribution here in this setting. So the local risk has this very nice expression here. And by this, we also find a very precise expression of the risk of the distributed ordinarily squares estimator. And why is it so nice? Because we now can also calculate the efficiency here. And here we see that the efficiency of the ordinarily squares estimator decreases linearly with the number of machines. So this is very, very explicit. And this means already in this simple setting, we have a loss in accuracy which decreases linearly with the number of machines. And this does not hold only for this simple setting here. This also is true for much more generous settings which can be found in this paper here, for example. Okay, so before I come to the setting where we have overparameterization and giving you some bounds, I cannot repeat enough, and we have seen this today already 2 times. So what happens again in the overparameterized setting for the single machine problem? Yes, we have seen this again. Here we have just a double descent curve. So this we know that when the dimension is precisely as large as the sample size, we observe a peak here, and then it decreases here in both directions. Okay, so but what happens now when we distribute the ordinarily squares estimator on 2 machines, for example? And so I think it's somehow quite intuitive and not super surprising that we again observe a double descent curve, but now we have a peak at points where the dimension is exactly as large as the local sample size. This means on this axis here, whenever the sample size is d times the number of machines, we will have a peak. And basically the peak is shifted to the right. And so this gives you a first intuition why maybe the naive approach, just doing an average of the ordinarily squares estimator, might not be a good idea. And we can also make this a bit more precise. In fact, under a certain set of assumptions here, we can in fact derive a lower bound for the risk of the distributed ordinarily squares estimator. So when we have that the dimension is exactly the local sample size, we observe peaks which are at least of this height here. It's just d over m. As a basic requirement we have here, which is maybe a tiny little bit of restriction of the setting, we need that the local data matrices have almost truly full rank. But under this very nice assumption, we can derive here a lower bound, which holds in both cases, by the way, for local over or under parameterization. And in fact, this is also known for the case of the single machine problem. That means m is equal to 1. And we derive exactly the same result, which was given in this paper here recently for the usual single machine setting. And this is just a generalization also to distributed learning. Okay, so this gives you a first idea that maybe something more is going on here and we need some more deeper insights. And one way to overcome maybe bad lower bounds or also double descent curves is regularization. And I want to give some more deeper insights here. Okay, so now we go to the overparameterized regime and we consider here richless regression or rich regression. So this means locally we solve now here this minimization problem, and we know that this also has here a closed form solution which involves here a matrix inversion. And again, I'm considering here just a uniform average of the local rich regression estimators. And typically, which this not only holds for the new regime here and also classically, analyzing the mean squared error of distributed learning algorithms always relies on tools which are developed for the single machine problem. So this makes our life much more easier because we can just now apply all the results which you already know for the single machine problem in the overparameterized regime. And for this, I provide you here a fact sheet with some results which has been obtained recently and which also we have seen a little bit today. So in the setting when the dimension is very large compared to the sample size, letting lambda tending to 0 in the limit, we obtain the minimum norm ordinarily squares estimator, and this can have a good generalization performance. And this is also known as benign overfitting or harmless interpolation. And maybe we learn a little bit more later today about this benign overfitting. And so here are some references which have considered this setting. So we also already know for the single machine problem that additional regularization can fail to provide any further information, and the optimal regularization parameter can even be negative. So this has been observed empirically and also theoretically in these works here. And we also observe some kind of self-regularization or implicit regularization. And this happens basically when the response is predicted by the high variance directions, while the low variance direction effectively performs some regularization or shrinkage. Okay, and we also know from some recent papers here that estimates on the tail eigenvalues of the empirical covariance operator help in controlling the mean squared error. And I want now apply all this known stuff here for the distributed setting. And basically, I'm following here the approach of these authors here to do this, because for me, it's, so as I read about benign overfitting, I really had a good feeling about the distributed learning setting. So at first, so my first thought, to be honest, about distributed learning in this regime was just, no, you should not do this. So because when you think of this ordinarily squares estimator, you immediately observe also double descent, and somehow this cannot be good. But in fact, when you know a little bit about benign overfitting, then so at least for me, it was a case that I got some hope that this could also be beneficial in the distributed learning setting. So because imagine in benign overfitting, it was shown that a large dimension is important for getting benign overfitting. And when you have a large dimension here, and when you start now to distribute your data, means that you locally increase overfitting, or you increase overparameterization. And this can be beneficial in a distributed setting. So this was my intuition behind this, and this was the main idea why I tried to follow the recent results here. Okay, and the main idea in these papers is that you fix an index, k, between 1 and d, and you only consider the subspace spanned by the top k eigenvectors of the covariance matrix here associated to the eigenvalues here. And then it is known that the minimum norm solution here has a decomposition in two parts. The first part is the component which we associate to prediction, and the other part is the component associated to interpolation. And so that's why I think it's also a good idea to to split the spectrum also in the distributed setting and try to see what happens. And I'm doing this for controlling these matrices here locally. So if you remember, so just considering here the local kind of empirical covariance, this matrix here appears in the evaluation of the ridge estimator, and we have to invert this matrix. So for us now, what we have to do is only that we need to control the condition number of these operators here, and we only do this for the components which are associated to the tail of the eigenspaces. So here, this index denotes just the matrix which is comprised by the last columns, starting from k plus 1 to d. Okay, and so my basic assumption here, which I need for today, is that for any local machine, the condition number can be controlled in a very nice way, and it is bounded by some constant uniformly in the number of machines with high probability. And then this can be done in some settings with nice distribution assumptions, is also shown in this paper. So again, here I'm just kind of stealing these arguments from these authors here. But it turns out very nicely at the end also for the distributed setting. Okay, and so let me now give you the most important result which we have so far. So under this kind of distributional assumptions here, for any lambda which is larger or equal to 0, we can upper bound with high probability the bias and the variance of our risk. So the bias consists now of two parts. So the first part here is associated to the remaining remaining components of the eigenvalues or eigenspaces. And the second part here is the prediction part. And here we see that, in fact, the tail sum of the eigenvalues is crucial, and also the regularization parameter. And here we also see that the bias is increased with an increasing number of machines. But I have some hope that we can at least control this by choosing lambda in a very nice way. Okay, so the variance also has two components. The first one is a variance which is associated to a finite dimensional problem. And then we again have here a part which belongs to the tail. Again, here we have the tail sum of the eigenvalues, which is important here. And so let me remark here that in the case of a single machine problem, we exactly recover the bounds which we already know from this paper here, and we just generalize it to the distributed setting. And so for now, when we want to derive some more concrete error bounds, we somehow have to choose the regularization parameter, and this can be done so in two very special cases, for example, and we have just to compare the lambda with the tail sum here, and it can be either larger or smaller. And I'm giving you now two very special examples, and I also want to derive some conclusion what it means now for efficiency in this setting. Okay, so the first special case is the case of small regularization, and I suppose here now that the tail sum is upper bounded by some quantity here, which involves also some eigenvalue, and this k needs to be smaller than the local sample size. Then we can show, if we choose the regularization parameter appropriately, we can bound the bias and the variance by some terms which look a little bit complicated at first sight, and I agree it is a bit. But the main important observation here is that these upper bounds no longer depend on the number of machines. And this here is really, really important and a very nice result. And so this is exactly the bound which can be obtained when m is equal to 1 under these choices. And for our prediction efficiency, this means this is just not decreasing in the number of machines, which is very, very exciting. And because I could not believe this result, and so I checked this a couple of times. So we run, of course, a small experiment to see if this can be true. And yes, this can be true. For example, if you have eigenvalues which decrease here exponentially, and you choose your lambda accordingly here, as I said in the result, then in fact we can obtain an efficiency curve is just a constant. So this is really a straight line, and this means in the setting where we have large overparameterization, we have no loss in efficiency in the distributed setting, and this is really great news. So on the other hand, in the second case, where we have a lower bound here for the tail sum of the eigenvalues, the efficiency can be upper and lower bounded by 1 over m squared. And this is now quite the opposite of what we have seen right before, right? This is much, much worse, of course. And so we have to choose the lambda also smaller than the tail sum here. Okay, so let me summarize here what we have found in a very special example of a spike covariance model. We also tried to show this also in simulations here. We have chosen our covariance matrix here in this very special way. This beta is just comprised of identical components, and our inputs are just normally distributed. And then, in fact, running some experiments, we see here an efficiency curve which is neither constant nor is it decreasing linearly. It's just even worse in this setting. So, and these two results are two very special examples of the setting here. And so let me briefly summarize what we found as some first insights here. The efficiency of distributed learning with uniform averaging in the overparameterized regime behaves very, very different compared to the classical underparameterized regime. So in case of small regularization, we observe no loss in accuracy, which is great news. But in the case of a spiked covariance model, we have a loss in accuracy with increasing number of machines, which is of order 1 over n squared. And this is much worse compared to the classical ordinary least squares problem, where we have a loss in accuracy, which decreases only linearly in the number of machines. And this is also different from the classical distributed kernel retrogression regime, where we have no loss in accuracy with an appropriate chosen amount of regularization and with a sufficiently small number of machines. So I hope I could give you some first insights into this topic. So this topic is very young, and there are much more open problems than I can solve currently. And so, yeah, so this is our first result which we have. And so thank you for listening.
This is a great work. I think that distributed learning in overparameterized setting is really like an interesting topic. It's a very promising topic, and well done for starting like researching this. So thank you very much. Let's all thank Nicole.